So today I'm talking about spherical objects in dimension 2 and 3. This is joint with Wahei Hara, who's here. And to sort of keeping with a slightly unorthodox view, I want to spend the first part of the lecture trying to explain to you why you should not care about this problem. And so it's the first section is motivation. So I'm going to have three settings in the talk. They're all quite similar, but just subtly different. And so the first setting is the minimal resolution. So G, a finite subgroup of SL2. And we form the quotient space, C mod G, and it's minimal resolution. Which is going to be called Z, curly Z. And so just to draw you a picture, I'll have some sort of surface, a sheet of paper with a unique singular point. And above it, I have a chain of curves. Let me draw you a picture. And so 1, 2, 3, say 4 curves. Let me label those curves. So C1, C2, C3, and C4. Now, each of these curves has a structure sheaf. And so each curve CI has associated structure sheaf. And for technical reasons, I'm going to twist by -1, but you can completely ignore that. It's more or less irrelevant for most of the talk. And this has a remarkable property, let's call it E, in that the X groups of this object in Z of E share the same cohomology as the sphere, or the two-sphere. So it's a C in degrees 0 and 2, and 0 else. And so why do we care about these objects? Well, there's quite a few reasons, but one of them is they generate you symmetries. And so Cecil Thomas implies that each E, so E is a OCI -1, gives rise to a spherical autoequivalence. I'm going to call that TI, which is the derived equivalence between the derived category itself. And these functors satisfy certain braid relations. And so if you sort of work through what that means in terms of categories, these generate a group action or a group homomorphism from the braid group, either of type A or of type D or of type E, depending on which example you're in, to the autoequivalence group of that. And so this is a very kind of classical kind of setting. And one of the questions that will sort of kind of hang around this for quite a while is question, so how many spherical objects are there? And so you have these curves that are spherical, and you can apply any autoequivalence you want, and it remains spherical. And so the question is, really, are there any ones that we somehow haven't thought of? So can we somehow classify these? Now, I'm going to lay my prejudice on the ground here. For many years, I just thought this was a terrible question. So there's 3 viewpoints on this question. One is from symplectic geometry, one is from algebraic geometry, and one is from non-commutative resolutions. And the symplectic geometry is a really, it's a good viewpoint here, because in symplectic geometry, if you can solve this problem, there are immediate applications. So you can say things about like the homology classes of Lagrangian spheres in topological spaces. And from this, you can get applications to stability conditions, and you can split homomorphisms, and you can do some pretty cool stuff. So from symplectic geometry side, if you can solve this problem, there is real applications. And from the sort of more algebraic geometry side, it's not so many applications. I mean, there are some sort of applications to stability conditions. So if you solve this problem, you should expect to solve that the stability manifold is connected, for example. But apart from that, it's not like this like really sort of drives much from the algebraic geometry side. But from the non-commutative resolution side, this is a very strange question. For many years I ignored it because I couldn't see, even if we solved it, what it would do somehow. And so the viewpoint of this talk is that it is actually a reasonable question, but it's only really justified by its answer and how that answer is obtained. So let me just quickly go and say why, if you want to solve this question, you've actually got to solve a more general question. And so the second setting is partial resolutions of Kleinian singularities. Now, it's sort of not wanting to say something which is tautologically obvious, but there's not terribly many Kleinian singularities. There's very few. There's basically 2 very small infinite families and 3 exceptional cases, and that's it. And since minimal resolutions are unique, there's only as many minimal resolutions as there are Kleinian singularities, which is basically none. And so what this partial equivalent resolutions do to you, it just generates you just a little bit more information, because there's loads and loads of these, or at least there's more. And so let me just do an example. So I have my 4 curves going to a point of my group. And let's just say I contract 2 of them. I get something which is a little bit singular. So this is my minimal resolution, and my partial resolution has got 2 singularities on it. And this is, I'm going to call this Y. The notation does become clearer later, kind of. So this here still has 2 curves, C1 and C2. Now, what's more interesting is that the spherical technology does not apply off the bat to this situation. So if you take the curve CI, C1, because X groups is somehow quite a local thing, kind of, you kind of expect, because the singularities are away from C1, you expect that to be still remain spherical, and that's true. And so that's, so OC1 is still spherical. And so you get an autoequivalence T1. And the problem now is that OC2 is not spherical. And I actually forgot to do the calculation this morning, but I think it's got unbounded sort of X group, so it kind of goes off increasing this. But one thing you can do is you sort of deform it slightly. You apply what's called non-commutative deformation theory, and you can still, from it, even though it's not spherical, you can obtain an autoequivalence, which I'm going to call T2, and these belong to the autoequivalence group of Y. And so it turns out, rather surprisingly, these braid, but not in the way you might think they braid. And so it turns out that the length 4 braid relation holds. T1, T2, T1, T2 is isomorphic to T2, 1, 2, 1. And the length 3 relation does not hold. And so what you end up with, this sort of knits together in the same way here, you get a group action of a braid group, but not the one you expect. And so you get the braid group of B2 to the autoequivalence group of Y. And again, I want to say something tautologically obvious. B2 is not A, it's not D, and it's not E, but somehow it comes up from these sort of partial resolutions. And in general, the object that sits here is not coxeter. It comes from some hyperplane arrangement that's just mildly more complicated. But in this example, I've chosen the easy one so I can write it down fast. And so the question here is that if you're interested in this question, you have to ask why you're interested in this question. And usually you're interested in it for stability condition reasons. But you know, stability conditions here also exist. They also have this as your Gawa group. It's exactly the same story. And so if you're interested in stability conditions and applications through that, you have to be able to generalize that question to answer some question here. Right? But you're no longer trying to classify spherical objects because the things that you want to somehow classify aren't spherical. And so the question is, what are we supposed to be classifying? Yeah. So what objects kind of look like these two objects there? So that's the second setting. And there's a philosophy that these, if you want to prove a result in these settings, it should also work for three-dimensional flops. So let me tell you that. And so in some ways, the question gets worse. So the third setting is threefold flops. And so this is now X. So I'm going backwards in the alphabet. Z's the minimal resolution, Y is the partial resolution, and X is a threefold. And so draw you a picture. Again, I got some level of curves. It doesn't have to be thinking configuration, but it's a three-dimensional variety. All right, it's contracting some curves to points, and there's technical assumptions that you can largely ignore. But ultimately, the cartoon picture looks very similar to this. Now, what's interesting in this situation is that the minimal model program tells you that you have to deal with varieties that are singular, right? So it's forced on you. You can't can't wish this away. This is a singular variety in general. And so again, you shouldn't be trying to classify spherical objects because the objects here have got unbounded X groups in general because of the singularities. So let's just say in here, so this has got, so if it's terminal Gornstein's the technical condition. And so e.g. smooth. So you can think of it smooth if you want to, but it's actually better to think of it singular because it sort of illustrates more how that questions are kind of the wrong question to think about. And so just to, again, illustrate to you roughly how crazy this goes, if I look at E, a structure C for one of the curves, and now there's a whole load of options. And so the X groups of this object, well, sometimes they can be spherical, right? So it is possible that C0, 0, C0. It can happen that they're spherical. And this happens if and only if it's a -1, -1 curve. So the normal bundle is of a particular form. This is a technical term. So the point is, of course, that -1, -1 curves, again, basically never exist, right? There's a unique example of the contraction with a -1, -1, a single one, not a universal value, just one. So there's only really one thing that has this cohomology. More generally, you get cohomology that looks slightly more like a lens space in characteristic P. And so this is if you're a -2, 0 curve. And then it gets more complicated. The sort of generic behavior is that the cohomology looks like that. If you're a what's called a -3, 1 curve, that's where all the action is somehow. And again, this is only in the case it's smooth. Otherwise, an absolute zoo of craziness. And so you got C, and it goes on forever. And this is if you're singular. And the question now is what are we classifying? Wow. So let me make it a little bit more precise and set some notation and then sort of say some results. Okay, so from now on, F is going to be either, so I'm just going to use F, either it's the minimal resolution, or it's the partial resolution, or it's a flopping contraction. Now, of course, these are kind of the same setting, right? I mean, it's like a partial is a special case of a full. But the features of the two of them are just mildly different. And so I want to keep them as separate. It's easier to state things here than it is here in general. And so I'm going to consider the category C, which is the null category, which is all those objects in the derived category of sheaves, either on Z, Y, or X, depending on your setting, such that the drive push forward is 0. And so this is called a null category. And one reason we're interested in this category, well, there's a few reasons. Well, it shows up at various places, like it's very natural again in symplectic geometry. It shows up at various different places, and the stability conditions and various things of this category are of interest. But from the viewpoint of my previous part, the key point of this category is it contains the objects that I am talking about. And so the curves above the origin all belong to this category here. Okay. And so there's one thing I want to say about this before continuing is that this category carries what we like to think of as a canonical T structure. And this is due to Michel. I'm going to use it in quotes because it's not really canonical, but it's a T structure, but very useful one. And so the drive category of sheaves in either Z, Y, or X, depending on your setting, is always the same as the drive category of modules on some non-commutative ring A. This is Michel. And there exists an idempotent E in A, such that the subcategory that we're studying here is actually corresponding to the category whose cohomology is annihilated by that idempotent. And so the idempotent is it's quite a technical thing, but it's got a benefit. The benefit is multiplying by an idempotent is exact functor. So things become just a little bit easier over here than they do over here. You're trying to get away from using this morphism because you have to take the derived functor, whereas this idempotent you just don't. It's somehow this side is in a technical aspect a little bit easier. But the point here is there's a T structure A mod AEA with heart. I should say in words with heart modules. Okay, so we're up to the point of my talk is that this category C looks a little bit complicated, but the point of the talk is that it's orders of magnitude easier than you think it is. Yep. So let's go to the result. So let C be as above. Okay, so you just zoom out a little bit and you try to sort of make sense of what's going on in these different settings, right? So we don't know what we're trying to classify. That's part of the problem. And so if you don't know what you're trying to classify, you try to do something more general first and then zoom in afterwards. So I want to write down 3 conditions on the board. So an X be an object of C. And there's 3 conditions I want to write down. One is that the X has no negative self-extensions. Now that's in some ways quite a weak condition. So every single sheaf or any single object in your Abelian category satisfies this condition. So it's in some ways quite weak, but of course you take a completely arbitrary complex, it is an assumption. And so the second thing you might be interested in is that X belongs to the heart of a bounded T structure. And the third thing you might be interested in, which is related to the sort of motivation, is that there's some element of the braid group or some sort of groupy sort of thing, such that, and some OCI minus 1, such that your object is actually in the orbit. Sorry, no. So some element of the standard heart and Y in the standard heart, such that X is actually obtained from the standard heart. And it's absolutely clear that 3 implies 2 implies 1. And the concept of the theorem is that they're all equivalent. So the following are equivalent. So everything in this category, every object in this category that looks like it should be in the heart of a T structure, a bounded T structure, is in the heart of a bounded T structure. I somehow couldn't believe this at first because it's a hell of a statement. I didn't know any situation where this was true. And so I want to sketch to you why this is true, or at least some sort of reasoning behind why you might expect this to be true. Gee, yeah, so very good. So, it depends on the setting. So in the minimal resolution, it's just the braid group, the standard braid group. Yep. In this situation here, it will be this group here. And in general, it's the group that sits, I'm trying to squeeze that under the carpet, but there's some pi1 or some Deligne groupoid sort of object in the background. But if you think just of the braid group, you're doing that. Oh yeah, sorry, that's very confusing. Yes, yeah, that's absolutely right. Yes, that is indeed confusing. Yeah. Sorry. Yeah. Well, the problem is it's coming later too, and so if I use another letter, I'm a bit nervous. So I'll put it in bold. How about that? Because then it looks like it's a groupoid, which it is actually, and so I can. It's a little bit cheeky. Yeah. Okay. Sorry. I was hoping not to avoid groupoids because it's first thing in the morning. I have to say, so in the threefold case, you have to look at all Crepont resolutions or all things obtained, and so in the movable cone, and it's the groupoid that comes from the movable cone. Can I explain it later? It's basically the obvious. It's the thing that generalized the braid group and sort of stuff. It's not actually important from the view of my talk. Really, one enough only if 2 is the kind of actual thing you should be thinking about. This is what I'm contesting. So I want to sort of argue as to why this might even be plausible. I'm going to get back to that. Yeah. Get back to that. So okay, so I want to sketch the proof of what am I going to prove? 1 implies 3 is probably a good idea. Yeah. Well, it's really 1 implies, well, it's kind of 2 or 3. So you take an arbitrary object, right? So we have X such that Homs, negative Homs die. Now, let's for a moment just try to visualize this object, right? It's a complex in this category. So X, like in Anna's talk, you shouldn't think of X as a small object. It's a monumentally large object. So you might have like a million here. And it goes all the way to x0, and it goes all the way up to x 9327152. It goes to 0. And I'm drawing this to just so you shouldn't think of this as being a reasonable thing to draw, right? X is just an object in a category. To draw this picture, you're already stating that the canonical T structure is somehow distinguished. And if you believe the theorem, it kind of is in some sense, but it really isn't distinguished. You have to somehow find another T structure to put it in. And if you believe the theorem, I appreciate I've given you absolutely no evidence to believe it, but if you were to believe it, there is going to be a T structure. So this is just telling you, with respect to the standard T structure, your object's a mess, right? It's over a huge homology degrees from here to here. But if you believe the theorem, there has to be some bounded T structure or some heart. And with respect to that homology functors, the spread is teeny weeny weeny weeny. It's just a single degree. And so what you're trying to find is you're wanting to find a T structure, T or heart A, such that the cohomology functors with respect to X are a single degree. So if you believe the theorem, this has to be true. And so the question isn't really about objects or about complexes. It's really just about how you're going to create a T structure with this property. Now, there's not a terribly a lot you can do. And so the idea is you're not going to be able to do this in a single go, right? You're not going to be able to say, this is the T structure, we've nailed it. And so you're going to have some sort of inductive argument. And usually what happens in these inductive arguments is you want to use the braid group or generators and relations. Now, of course, is a disaster because you start thinking about generators and relations, it's all very, very, very specific. And so we want to find a way of getting to this heart without necessarily knowing exactly each step, how we get there. And so this is appealing to some minimal element in the process. Let me try to explain that. So you want to improve your complex. So your complex here is going from some degree, which I'm going to call A, to some other degree, which is B. And so I'm going to write X belongs to, its cohomology is between A and B. And we want to test T structures with different homology groups to try to improve this. If you improve the AB bound, you can induct. And so what we do is we, notation, we consider T structures with hearts A, which are intermediate. So between our standard heart, somehow A, and our standard heart is shifted by 1. I've just realized I don't know my sign. Let's just call it +1. I pretend that's correct. And so, so you're going to use these as your test objects, and you hope that something in here improves the situation. I want to give you a heuristic why that's probably false. So this T structure here is corresponding to the identity functor. And if you imply the identity functor of this complex, you're not going to improve it. This T structure here corresponds to the shift functor. And so if you apply the shift functor to the complex, you're not going to improve it. And so you're hoping somehow in here that one of these improves it. And so what does that mean? And so you study this, all those, so these are called intermediate T structures, T, such that HI, also of T of X, sorry, X, yeah, very good. It is wrong. Yeah, let's just pretend this is correct. This first thing in the morning is A, comma B. Yeah. So does it make it worse? So this T structure here, I've got my signs wrong. This T structure here shifts it in one direction, and so it actually moves out of this range. Where this T structure here does nothing, and so it keeps it in the range. And so some work and some don't. And so some of the T structures have this property and some don't. But the point is, this is a finite set And why is that a finite set? Well, essentially because if you're in the coxative setting, these things are bijection with the Weyl group, and the Weyl group is finite. In a non-coxative setting, you have to do a little bit of work, but this is a finite set. And just like in many situations in maths, for example, Roman stuff on real stability conditions, there's an order on these T structures. It's a poset. It's an order. So it's not just a finite set, there's an order on them, a poset. And nobody remembers what the order is. It's either if you can tilt one to the right by a symbol, it's larger, or the left. Nobody remembers, but there's some order, right? The order is again irrelevant. So if you have a finite poset, it's kind of embarrassing. All we're saying, this is our key insight, finite poset has a minimal element, right? And we're just going to pick it. And that improves the situation, and then we induct. Yep. And so that's the proof. Let's just write that down. And of course, it doesn't have a unique finite poset, but you have a unique middle, but you don't care. There's not going to be a unique way to get there. And so you don't care if it's unique. There is a minimal element. And so you pick a minimal element, T min, and then you argue that the cohomology with respect to that T structure is actually improved. So it's A minus 1, plus 1, plus 1, B. Yeah. And so this part of this actually, again, if you're crazy enough to believe it, this is actually really easy. This is the only part where you actually use the X vanishing, and actually you don't really use the X vanishing. The only thing you use is that there's no homomorphisms from the top cohomology to the bottom cohomology. And that follows by basically a spectral sequence, because if there was such a homomorphism, you get a negative X. There's a non-spectral sequence argument. But that's that. So that's the theorem. And 25, perfect. I want to just run through a corollary, and then I'll address Sasha's question. And so the corollary to this is that C is above, and then the following are equivalent. And so the first condition is the same. There's no negative X. But you added just one more condition. The Homs in degree 0 is the complex numbers. So it's an exceptional object. And then the second condition is, in just that X belongs to the heart of a bounded T structure, is that X is the simple, is asimple. The T structure. And the third condition is actually what sort of the motivating question was. There's some element G in our group oid in general, and some OCI minus 1, such that your object is actually in the orbit of that object. And so this corollary is telling you that of all the sort of cohomology stuff I had at the beginning, it's basically all completely irrelevant. The only conditions you need are negative X groups, and Hom spaces being one-dimensional. And you get a complete classification from this. And from this, there's various corollaries. So in the Kleinian singularities case, minimal resolution, this does actually classify spherical objects. But basically, it classifies much more general things. And this, in the case when spherical objects are relevant, you can use this to classify it. Okay, so this is where we're up to for a while, and then we started thinking a little bit about applications. And again, the expectation is if you can do a theorem like this, then it should have applications to stability conditions. So you should be able to use theorems like this to prove that stability manifold is connected. Now, I was running through the proof of this, like Ishii, Ueda, Wahei Hara have this like very fancy deformation argument. It's a little bit insane, really, and it's kind of madness. I was reading this thinking, surely can't be somehow what the point is. And Anon explained this to me very eloquently in the tram yesterday, that when you prove quite a surprising result, at some point you have to step back and actually ask yourself, why is this true? So it's not obvious to me that this should be true. And so I was a little bit confused. Now, I want to run a mental thought experiment past you, which is related to Sasha's question. If you fantasize just for a moment that every T structure, the heart is finite length with finitely many simples, then that heart is just controlled by the sum of the simples, right? Yeah. And so you add them together, you plug in the theorem or the previous theorem, I don't know where it's gone here, and in particular, you get that those objects can be made to be inside the standard heart. But if those objects can be in the standard heart, the whole T structure can be, and that can only happen if they're the same. And so you're crazy enough to believe that every heart in this category is finite length. And then what this is really doing for you is it's actually classifying bounded T structures. And that's the next result. That's exactly what's true. This is basically the technology of this is really classifying T structures. So let me write that down. And so the theorem is, yeah, so A is the heart of a bounded T structure. And number two is that A actually is isomorphic to the image of a standard heart for some G in your group oid. And so in particular, all hearts have finite length. And so the proof of this is like alarmingly similar to the proof of that. But the only thing you've got to be super careful of is that you can't deduce this until the end. And so you have to be very careful that you're not dragging objects. You've got to take the whole T structure all the time. And so the technology used to do it is just a little bit more involved, but ultimately the same strategy is you have these intermediate ones you're testing objects with. That's still a finite poset. You still choose a minimal thing. And with a little bit extra work, this comes out for free. And so this gives you the corollary, which is the one I actually was aiming for all along, was that the stability manifold of C is connected. And it's also contractible and various other things. But now, what I like about this proof is just insane. So you want to know a stability manifold is connected. So what's our proof? Our proof is you don't have any of this fancy deformation technology. Your proof is the following. You take a stability condition. Well, that corresponds to a T structure and a central charge. We know all T structures and we know all central charges. We can literally write down every single stability condition on this category, and that's visibly connected. And that's the proof of the corollary. So you don't need anything fancy about stability conditions. It's a purely homological result. Okay, so I have absolutely no idea when I'm going to finish. So let's finish now. And so there's corollaries to this too. Partly in symplectic geometry, myself and Ivan have got various sort of corollaries of splitting of the pure braid into the symplectic mapping class group. And there's various other corollaries too. The technology isn't actually just confined to this category C. You know, I'm giving a talk here, but it generalizes to like the derived category of silting discrete finite dimensional algebras, for example. The same technology holds. And basically, as soon as you have some sort of finiteness in your category, and this is kind of, so Yama would call it a tall tilting finite, but you have some sort of finiteness in your category like this, I used to expect similar results to hold. So I'll stop there. Thank you very much. Thanks.